Assalamualaikum warahmatullahi wabarakatuh. So welcome back to my video. So let us continue with this another work example where the question says 2400 volt, 460 volt. So this is obviously a step down transformer, okay, from 4400 down to 460 volt. So this is the S or the apparent power rating, 25 kVA. So transformer has a series leakage reactance of 37.2 ohms. So you see here the location of the ZT, the series leakage reactance, as referred to high voltage side. So it is clearly mentioned over here that the transformer series leakage reactance is being referred to the high voltage side. High voltage side means at the primary side of the transformer. Okay, so it's supposed to be at this zone. So P primary and S secondary. So a load connected to the low voltage side, of course, this one. All right, so let me write the ratio. So this is 2400, all right, volt, okay, down to 460 volt. Okay, the low voltage side of the transformer. Good. A load connected is observed to be absorbing 25 kilowatt here. Okay, and then unity power factor means power factor is 1. And the voltage is measured to be 440 volt. The load voltage or the voltage of the load is measured as 450 volts. So calculate the corresponding voltage and the power factor as measured at the high voltage terminal. So high voltage terminal at the primary, of course. Okay. So we are ordered to calculate the corresponding voltage over here, VP. Okay, question marks. What's the VP? And then the power factor as measured at the high voltage terminal as well as the power factor. Right, question mark. So let us start with the solution. So first divide the circuit into zones and choose two base quantities for each zone. So apparent power supplied to the load is S equal to PL over PF. So this is the equation or the formula for supplied apparent power to the load. Right? Since we have the power factor of 1, okay, so we can basically, here 1, so you can basically take the value of S, okay, which is 35 kVA. So divided by power factor, which is equal to 1. Okay, so from there, the load apparent power is equal to 25 kVA. So this is not kVA, but this is actually watt, right? So we take from P. So this is power, the active power or the real power of P. So therefore, let base VA for the two zones be 25 kVA. This is let S base 1 equal to S base 2 equal to 25 kVA for both zones. Okay, then let V base 1 equal to 2400. So this is from the ratio. Okay, the transformer rating, ratio rating. Okay, and then we have the second base, which is 460 volt. Okay. So now the second step is to calculate the other two unknown base quantities. So we have done with the first two quantities, which are S and this S and the base for both zones, both part primary as well as the secondary. Now we continue with another two unknown base quantity. Basically this is Z and I. Okay, so altogether we have to find, again I would like to recap, four base quantities. For elements, we start with S and V. Okay, and then later on from this S and V, we try to manipulate the equation in order to get Z, the impedance, and I. So it's gonna be a very direct forward equation where we have again Z equal to V squared over S and I base equal to S over V. Okay. So you have to memorize, you have to remember these two equations. Okay. So now substitute the value of V base 1, the one we have picked earlier, okay, and then S base 1, okay, 25 kilovolt ampere bar. Okay, so this is the value of Z base 1. So I base 1, the ampere value. So S base 1 divided by V base 1, which is 2400 or 2400 volt. Okay, so we obtain the value of I base 1, that is 10.417 ampere. So similar process at zone 2, the secondary part of the transformer. So we have Z base 2, as well as I base 2. Substitute the equation P over S or V squared over S as well as S over V. Then substitute of value, the value here and here, okay, value of S base and also the V base. Okay. Then this is the final value of I or Z base 2 and also I base 2. So convert the given SI quantities into per unit quantities and draw the per unit equivalent circuit. So this is the equation, all right, for per unit or single phase of power. All right. So remember, this is a single phase of power. So everything into per unit quantities, and we are going to draw the per unit equivalent. Thus, the P, however, is reflecting the single phase. That's why we don't have square root 3 equation. Okay, we don't have, this is for three phase. Okay, but in this particular example, so we convert everything into single phase. So now square root 3 equation at this formula. Okay, so we arrange, we have IL equal to PL over VL cos theta or power factor. This is cos theta. So PL, P 25 k watt, okay, over 450. This is the load voltage, okay, and then this is the power factor at the load. Okay, so everything occur at the load. Remember, so L stand for load. Okay, this is taking place at the secondary part of the transformer. Okay, all happen here, right here. So we have the IL. We are about to calculate. So we have the PL over here over VL over here multiplied by cos theta or power factor. Right? And then giving IL equal to 55.556 ampere. So therefore, per unit load current is ILPU. So we have seen the actual value of load current, okay, here, and then we divide by I base 2. Remember again, you must make sure you select or pick the right value of I base 2. Don't get confused with the I base 1, I base 2, I base 3, etc., etc. Okay, so you must make sure in which region or in which zone you are working in. Okay, in this particular case, IL, so IL is referring to zone number 2. All right, so you must pick I base 2, which is 0.348 ampere, and giving us this value of ILPU. Okay. Now per unit load voltage, so similar process, we have the PU, we have the actual, and then the V base 2. So this is what we have picked in the beginning of the analysis. So this is the load voltage and giving us the value of PU load voltage. So the PU transformer impedance is, so this is again the transformer ZT-PU, ZT actual over V base 1. So remember base 1, the transformer impedance, is here, is referred to the, I repeat again in the different color. So the leakage reactance of the transformer is referred to high voltage. So when we come to the circuit drawing, so you see that ZT is located at the primary side or primary zone of the transformer, zone number 1. So you must refer this to base 1. Okay, so here we go. So ZTPU is referred to the high voltage sides, meaning at the zone number 1, and we pick Z base 1 or Z base 1. Okay, as the base value. Substitute the value, the actual. Okay, this is from question. So this is from question. So this is what we picked earlier, or we calculate earlier using the formula of S and V. Then finally we're able to generate the value of ZT, the transformer impedance. Okay, PU. So therefore, from here, we can simply draw the circuit or the equivalent circuit. Okay, we start with VP PU. Okay, so this is the transformer impedance. So we have the load current PU as well as the load voltage PU. So everything in PU and connected in simple series circuit. To solve the PU circuit for VP or the primary voltage, okay, or the source over here. So application again, the KVL, Kirchhoff voltage law, to the above circuit leads to the per unit voltage equation. So we have VP minus IL ZT over here. So we have here also the same current, the same level of current, IL, since all the components are connected in series. So we should have here the same level of ILPU. So multiplied by ZT. So the voltage drop across this transformer impedance as well as the load. Okay, so this is a V. Let's say we name it as a VT for the voltage drop across ZT. So as well as the ZL over here, the load voltage drop. Okay, so we name it as VL. Okay, so we do have the VP, okay, the source over here, minus VT minus VL. This is equal to 0. Okay, in a closed loop like this. So minus VP is the same thing. So minus VP plus ILPU ZT plus VL PU. So since we have calculated the value of VL directly, so we don't have to multiply the IL with Z or impedance L. Okay, the load impedance ZL. Okay. Then therefore, so we have VP equal to, again, to rewrite the equation and substitute all the value quantity such as IL, VT, as well as VL. Okay. So by solving this, you now get the VP in PU, okay, the primary voltage or the source voltage of the transformer. Okay. in P, of course in PU. So now you convert the per unit primary voltage to actual value. How? So just copy this value again, the PU multiplied by base over here. Okay, just multiply by its base. Okay, base of course P primary base 1. Okay, remember base 1 is referring to the primary part of transformer. That is 2400 or 2400 volt. Okay, so here is the actual VP we finally obtained. So now the phasor diagram. So by having this result, so the VP out actual, so we can easily understand that the phase angle here is actually between I and V. Since the value is positive, when you come to the phasor diagram, meaning that V is leading I by 9.55 degree here. Okay, 9.55 degree. So this is I. If the answer is negative over here, if the answer is negative like this, simply something like this, so we know that the V is underneath I by a negative 9.55. Here, this is I. Okay, this is V. For the negative, the red color one. Okay, if negative. And here, let me go back to the blue color. What happened? Where is the blue color? So since V is positive, mean heading or reading I, but it comes to the power factor, you must refer to the position of I itself. Okay, the I. So in this example, power factor is or the primary current lags behind here. Okay, it is lag behind. IP equal to I load. Okay, it is lagging. It is lagging behind V. Okay, so we can say that the input of the transformer, okay, at the primary part, input has a lagging power factor. So the input power factor is, so PF, so again, this is input, this is actually at the primary. If you can recall the question, they ask you to calculate the power factor at the primary zone or at primary part. Okay, meaning the input part. So primary power factor equal to cos 9.55, 0.986. So this is lagging. Alright, this is another example. So given Vs equal to 220 degree X line, 2 ohms, Z load equal to 0.9 plus J 0.2. Again. Okay, all right. So we continue with the this question. So you can see X line 2 ohms, Z load 0.9 plus J 0.2 again. So truth transformer in the two transformer circuit shown below. So we have a special example over here. Since we have two sets of transformer, so we have transformer number 1 over here. So this is transformer number 1. This is transformer number 2. So then so we have to draw the per unit circuit, labeling all values. So determine the per unit load current and the actual load current. Okay. So let us interpret this circuit. Okay, since we have two sets of transformers, so overall we can divide it into three zones. Zone number 1, okay, we have zone number 2 and zone number 3. All right, so VS become our source as well. Okay, this is the coil of transformer number 1 with the ratio rating. Okay, so this is also can be our turn ratio, which is N. All right, so here simple, here also same, so we can actually calculate the turn ratio. This is equal to 460, all right, for over 115. Okay, so I'll calculate the first one. So this is 240 over 480. Okay, and then the apparent power value S and S is the value. So we have ZT1. So this is the impedance transformer. The first transformer is J0.768. And then this is the second transformer impedance. Impedance of transformer again, ZT2, sorry, J1.058 ohm. So this is line impedance. Okay, so the line impedance is identical with their identical value. Okay, right, then okay, solution, select base voltage and VA. So with more than one transformer in the circuit, we are free to choose either kVA rating. Let's S base 1 equal to S base 2 equal to S base 3, which is 30 kVA. All right. So the value of Z base should be chosen in the three zones to match the ratio of the voltage rating on either side of each transformer. So since we have three zones over here, okay, so we mark zone number 1 again, zone number 2 and zone number 3. So from here, so we must choose properly the V base. So this is no problem. This is obviously 240. So base number 2, so no problem. This is 480 if we refer to the ratio. Okay, here, okay, the voltage rating ratio. So zone 1, 240 for the V base. And then zone number 2 here is 480 volt. Okay, sorry, I forgot the symbol, the unit volt. Okay, here. But when we come to zone number 3, so the problem start to happen because we have the ratio of 460 here. This is 460. Whereas our zone number 2, so we have decided to pick 480. All right, 480, but here 460 at the primary part of the transformer 2, the incoming part, okay, or the input part. So from here, in order to find Z base 3, okay, Z base 3. So what's the, it's not Z base 3, sorry, this is V base 3, okay. So we must match the ratio again. So the ratio of N, all right. So N, so equal to 401.15. So once we come to the V base 3, so we must do the same process. We must match the ratio. So we have over here base 3, okay, V base 3. This is equal to 460, all right, divided by, sorry, 480, not 50, here to here, all right, here to here, okay. So we take 480, this is Z base 2. So we must divide by the N, this N, okay, the ratio. in order to get the V base 3. So this is how they done it. So we have V base 3, equal to V base 2 divided by N2. So this is the turn ratio for transformer number 2, where N2 equal to turn ratio of transformer 2. So this is 460 over 115. Therefore, V base 3 equal to V base 2 over N2, and this is 480 divided by 460 over 115. So this is equal to 120 volt. So this become our V base 3. Okay. And this is a straightforward calculation since we have done with S1, which is equal, again I repeat. So this is just to recall what we have calculated earlier. So we have done this. So we have done also VB1. So we have done VB2, and we have done V base 3. Okay, oh, sorry, this is B and B and B. Okay, and then I base 1, I base 2, okay, I base 3, all calculate using the equation. Okay, and then B, Z base 1, Z base 2, Z base 3, again using this equation. Okay, it's again direct forward calculation. Okay, so ampere, 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 ohm, ohm, and ohm. So transform the circuit quantities into per unit values. So ZSPU, ZS over V base 1. So 220 is the source value over here. Okay, the input value. So divided by 240. So if you go back to the circuit, so the value is given here. This is 220. This Vs. Okay, so I mark it here, Vs. So base 1. So this is taking place at base 1. So line PU, so you may refer to base 2, alright, because line is located here, right, between transformer 1 and transformer 2. Okay, occur from transformer 1 to transformer 2, and between transformer 1 and transformer 2, there is a line over here, transmission line. So which is impedance. Okay, between transformer 2 as well as the load, so there is another impedance over here. Okay, so both is having the line. Okay, so base 2 over J0 7.65. Right, so this is from question, the actual impedance value. So Z load PU, load, of course this is taking place at base 3. Okay, the actual Z load over Z base 3. Okay. Oh, before I forgot, since we have 2, this is 2, we have 2 multiplied by X line PU. So everything in this circuit is referred to zone number 2. Alright, this one also. Okay. So we have seen in the previous example or in previous video that regardless which part or which zone your transformer is referred or being referred, so it doesn't really matter. Okay, in this particular example, since we have the middle zone, so it seems that this middle zone is dominating both transformer. Okay, because at the left hand side of the zone we are having transformer number 1 as well as transformer number 2. Okay, so this is to show that this is dominating both part, and the other reason is because this line is actually carrying the highest voltage. All right, so 480, 450. Okay, so this means the Z line from zone number 3 is now being referred to Z or zone number 2. Okay. So this is the reason why we have Z base 2. And this is applicable for both zone, this value. So for zone number 2, plus zone number 3. So calculate the transformer impedance. So similarly, everything is being referred to base number 2. Okay, the middle zone. Either it is Z impedance or transformer impedance 1 or transformer impedance 2, the second impedance. Okay, so we have different values, 0J 0.76 for 68, sorry, J 1.0558. Okay, so you can see these two here is now being referred to. Okay, the Z is referred to here as well. This is here. Okay. All right, now draw the available per unit equivalent. So we have done with all the SI transformation or equivalent PU. So now we have VS, we have ZT1, okay, the transformer 1 impedance. So we have line, the first line impedance. So we have the second transformer impedance in PU, as well as the X line or the impedance, the line impedance of second line. I mean for the second transformer, as well as the load impedance. All together are connected in series. Okay, this is the closed loop. We can simply understand how to represent. Okay. So calculate the per unit load current. So we have the here the VS 0.9167 divided by all the impedance value. Okay, so this is for load. Okay, this is I believe for ZL. Okay, this is for line number 2. Okay, so this is Z of T number 2. So this is Z for first line, and then this is Z for transformer 1. Okay, and then this is the I load PU 0.425 minus 29.565 PU. So calculate the actual load current. So we have this value again multiplied by I base 3. Okay, why I base 3? Due to the load. Okay, location. Okay, actual load. So I base 3 we have seen earlier. So this is 250 ampere. Okay, thank you very much. So in the next video, we will continue with the percent impedance of transformer. So how we analyze, we calculate the specific impedance percentage or percent impedance of the transformer according to the nameplate given over here. Okay. Thank you very much. So I see you again.